Hi, in this video we're going to be proving that the complex numbers with pointwise addition and multiplication as defined below, a plus bi times c plus di equals ac minus bd plus I times ad plus bc, is a field. So to prove this, what we're going to do is we're just going to check all the field axioms and make sure it satisfies every one of them. So we're going to start doing this by proving that the complex numbers with addition forms an abelian group. So let's start by checking what I like to call property 0, the closure property. So we just want to make sure that if we add two complex numbers, we still get a complex number out. Next, we're going to check associativity, meaning we can move the parentheses around however we want and we'd still get the same thing. We're going to check to see that there's an identity element, an element that no matter how we add it to something, we still get that same thing out. We're going to check the inverse axiom, make sure that every element has an inverse. And finally, we have to make sure it's an abelian group, so we're going to check commutativity. So let's go back and check to make sure it's closed. Now, if we take any complex number, a plus bi, and add that to another complex number, c plus di, we get a plus c plus I times b plus d. Since a, b, c, and d are all real numbers, so is a plus c and b plus d. So we can check that off and we have a complex number. Next, let's check associativity. So let's go ahead and make some space for ourselves. And what we want to check is no matter how we move the parentheses around, we still get the same answer. So we'll start by taking a plus bi and adding it to the quantity of c plus di and e plus fi. So by adding this and doing some algebraic manipulation, we'll end up getting that we can just move those brackets over and get a plus bi plus c plus di all plus e plus fi. Now let's check to make sure that we have an identity. So we'll give ourselves some space, and we're going to claim that 0 plus 0i, one way of writing a complex number is by a coordinate. I'll go back and fix that in a moment. But we're claiming that 0, 0, or 0 plus 0i is the identity. So we'll check it by taking a plus bi and adding it to 0 plus 0i, making sure we get a plus bi out. And then we're going to add 0 plus 0i to a plus bi and making sure we get a plus bi out again. Next, we're going to have to check our inverses. So given any a plus bi in the complex numbers, we're going to claim that negative a minus bi, or negative a plus negative bi, is the additive inverse. So all we have to do here is we have to check that a plus bi plus negative a minus bi is 0 plus 0i, and it's the same thing if we add it in the opposite direction. Finally, we're going to check the commutivity property to make sure that this is abelian. So we're just going to take a plus bi, c plus di, two generic complex numbers. We're going to add them, and then we're going to use the commutivity of the real numbers to flip a and c and b and d, and then just use the definition of addition again to split it back up, and we get commutivity. So we finally come to the conclusion that the complex numbers with addition defined pointwise is an abelian group. Okay, so next we're going to have to check that C without the additive identity, which is 0 plus 0i, is an abelian group. And just for reference, I rewrote the multiplication rule for C in this instance. So to show that it's closed, that's the rule for multiplication. And since a, b, c, and d are all real numbers, we have that AC minus BD and AD plus BC are all real numbers. So it satisfies the condition for being a complex number. Right, next let's look at associativity. So we want to show that some complex number, a plus bi, times c plus di times e plus fi is the same as the quantity of a plus bi times c plus di, all times e plus fi. So to do that, we're just going to multiply everything out, and the steps are shown on the screen. Okay, so once we've multiplied them both out, let's compare the left-hand side to the right-hand side, or one product to the other product. So I'm just going to copy what we had and paste it below, and we're just going to match up terms. So we see ACE match, ADF matches, BDE and BCF, as well as their signs. And similarly for the imaginary component, we see the ACFs match, the BDFs match with their signs, the ADEs match, and the BCEs match. And since they all match, we can say that this operation is associative. Next, we have to show that there's multiplicative identity. So what we're going to do is we're going to claim that 1, 0, or 1 plus 0i is the multiplicative identity. So what we're going to do is we're going to take any complex number, a plus bi, and we're going to multiply it by 1 plus 0i, and we're going to multiply 1 plus 0i times a plus bi. And what we're going to show in both cases is that we get a plus bi out using our rule for multiplication. And since they both give us what we started with, we can claim that we have an identity. So the next step is to show that we have an inverse. So given any complex number, a plus bi, we claim that a over a squared plus b squared plus negative b over a squared plus b squared is our multiplicative inverse. And to show this, what we're going to do is we're going to take a plus bi and multiply it by our alleged inverse and show that we get 1 plus 0i. And then we're going to take what we claim to be the inverse and multiply it by a plus bi, the opposite way, and show that we also get 1 plus 0i. And finishing up, we see that the opposite multiplication gives us 1 plus 0i, so our claim for an inverse was true. Finally, we have to show that our structure is commutative. So all we're going to do is take a plus bi and some other complex number, call it c plus di, multiply it in one direction, and then multiply it in the other direction and show that we get the same product either way. So the next step is to show that these two are equal, but since the real numbers are commutative, we can just switch the a and c to get ca, b and d to get db, and the same with ad and bc. Therefore, our structure is commutative, and finally we can conclude that the complex numbers without the 0 element and multiplication is in fact an abelian group. So now we have to connect our addition and our multiplication. So we have to show the left and right distributive laws. So we'll start by showing the left distributive law. And to do this, we're going to do the same thing we did to show associativity. We're going to look at the left-hand side of our equation and compute it out. And then we're going to look at the right hand of our equation and compute that out. And we're just going to compare each of the terms in the imaginary and the real components. And we're going to see that they are equal. And now that we've multiplied them all out, all we have to do is a quick check and confirm that the real and imaginary components are the same, recalling that we can move real numbers around how we would expect to move real numbers around. Next, we're going to show the right-hand distributive law. So we're just going to take a plus bi plus c plus di and multiply that whole quantity by some other complex number, e plus fi. And we're going to do the exact same thing to show that they're equal as we did with the left distributive law. Okay, and now that we've multiplied it all out and added everything together, we can see that by comparing everything in the real and imaginary components, we get what we wanted. So finally, after everything that we've done, we've shown that it's an abelian group with addition. If we take away 0, we get an abelian group with multiplication, and we have this nice distributive law. We see that it satisfies all the field axioms. And therefore, we may conclude that the complex numbers with addition and multiplication, as we have defined it, is in fact a field. Thank you for watching. I hope you have learned something about complex numbers today. Thank you.